Welcome to Lesson 5.2, Properties of Rational Exponents and Radicals, Part 2. In the last section, we worked a lot with numerical values, simplifying expressions and radicals. Most of those involved numerical values, fifth roots, fourth roots. You saw all that kind of stuff, multiplying, dividing, rationalizing denominators. We're going to start off this lesson by taking a look at how to do some addition and subtraction of radicals. The most important thing to remember when you're adding or subtracting radicals, that in order to do anything with that, you have to make sure that the radical number matches, that you're taking the nth root of the same numerical value and that value is the same. So if I'm looking here in example A where I have the fourth root of 10 plus 7 times the fourth root of 10, if these numbers do not match, you can't do anything with that. So they both have to be the same number. Like if this was the third root of 10 instead of the fourth root of 10, we actually would not be able to add them together. But because they are the same, this problem is actually really easy to do. If I have one fourth root of 10, you have to remember there is an unwritten one there. So I have one fourth root of 10 plus 7 fourth roots of 10. That gives me 8 fourth roots of 10. And that's all there is to the problem. There's no need to do anything else. It's 8 fourth roots of 10 and you're done the problem. Going over here to letter B, notice that this is the 7 to the 1/3 and 7 to the 1/3. If I was thinking about this a different way, that's actually 5 times the third root of 7 plus 6 times the third root of 7. So the fact that I've written this with a rational exponent up here, that just simply means the same exact thing that I've written down here. We need to be comfortable with using 7 to the 1/3 power and knowing that that really means the third root of 7. So when I'm doing this problem, these numbers here in the parentheses need to be the same. So this is like saying 5, 7 to the 1/3 plus 6, 7 to the 1/3. And what I can do is I can just add these numbers together and I get 11 times 7 to the 1/3. And again, that's like the same exact thing as 11 times the third root of 7. Subtraction is going to work exactly the same way, but you'll notice something here. You'll notice that these numbers do not match. The number underneath the radical isn't the same. I have the third root of 54 minus the third root of 2. And you may be thinking, oh, I can't do this problem. There's nothing else to do. But that's not exactly what's going on in this particular problem. If you simplify this radical, or simplify both radicals, now the third root of 2 doesn't need to be simplified at all, but the third root of 54 I can actually simplify. When I simplify that down, let's see here, that's the third root of 27 times 2. The third root of 27 is 3, and then I'm left with a third root of 2 underneath the radical. So let's see here, this problem now is 3 times the third root of 2 minus the third root of 2, which gives me 2 times the third root of 2. See, that actually we can do. Looking at the original problem, you might not have seen that you could actually do this. Part D is the same thing, same idea. If you want to pause the video right now and give that a try, go for it. Okay, so I'm going to do the same thing. I'm going to simplify that. And 48 is 16 times 3. Okay, let's see here. And let's say the fourth root of 16 is 2. So this turns into 2 times the fourth root of 3 minus a fourth root of 3, which just gives me 1 fourth root of 3. But we actually don't need to write that 1 at all. You can actually just forget that 1 was even there and just write it as the fourth root of 3. That answer is good enough. So again, when you're adding and subtracting radicals, it's important that the radicals match. If you think of it like terms, you'll never go wrong. But that's pretty much all there is to adding and subtracting. What we're going to take a look at next is simplifying radicals. Now, from the last section, the radicals that we were simplifying didn't have any variables involved. But what you're going to see with this set of problems is some variables underneath of the radical. And it's not really a big deal. What we're going to look at when I'm looking at A, part A here, the third root of 27d to the 12th power. I'm going to split this up because the third root of 27 I'm comfortable with. I've done that before. The third root of d to the 12th, I might need to think about that a little bit more. So the third root of 27, that's 3. But what's the third root of d to the 12th power? Well, if I think about this, And I know a lot of you like to do factor trees. When I write this out, my gosh, that's going to be 12 D's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I need two more, 11, 12. And when I'm taking the third root of something, what I'm looking for is I'm looking for groups of 3. So how many groups of 3 go into 12 of these D's? Now if I look at it, I have 1, 2, 3, 4. So the third root of D to the 12th is actually the same thing as D to the 4th. Now, I got to be honest, I'm not going to do this every single time. What I simply see is I see the math. I see that if I have 12 D's and I'm going to divide it into groups of 3, that I do 4 because 12 divided by 3 equals 4. And that's a really great shortcut to be able to simplify a radical. So what this is going to turn into is then 3 times D to the 4th. And that's it. That simplifies down fairly nicely. When I do part B, again, don't try to rationalize the denominator here, especially when you can do the math that's here. If I divide this up, I have the fourth root of x to the fourth over the fourth root of y to the 16th power. And again, if I think of this division, right, this idea of division, I know that 4 divided by 4 equals 1. So on the top of this fraction, the fourth root of x to the fourth is just going to turn into x to the first power. But again, I'm not going to write the first power. On the bottom, if I think 16 divided by 4, 16 divided by 4 is 4. So the fourth root of y to the 16th is going to turn into y to the 4th power. That is my final answer for this one. Things work out really nicely when these numbers are divisible, when the exponents underneath the radical is divisible by the root number that we're taking the root of, or the index number. So like 4 and 16, 16 can, or 4 can go into 16. But what happens if it's not? Let's take a look at this one. Example C, the third root of 2, a to the 13th, b to the 3rd, c to the 8th. Okay, first thing I'm going to do with this is I'm going to divide it into different parts so we can take a look at each part individually. And that's kind of the way you're going to have to do this. So we'll look at the third root of 2. We'll look at the third root of a to the 13th power, the third root of b to the 3rd, and the third root of c to the 8th. And each one of these we're going to deal with differently. So the first one, the third root of 2. I can't do anything here. That is done. That's simplified already. That's going to be part of my answer. So I can't do much here. So I'm just going to skip over that and we'll go to the next one. The third root of a to the 13th. Now again, if we think about that divisibility thing, I know that 13 divided by 3, whoa, what is that? Well, it's 4, isn't it? It's 4, but it's not evenly because that's 12. So it's 4, and we have a remainder of 1. That idea of a remainder is going to be really helpful when we simplify the third root of a to the 13th. When I simplify the third root of a to the 13th, I'm going to have a, oh, let's write this out. I think that this might be helpful for us to see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And again, it's a third root. So I would look for my groups of 3. Let's hear 1, 2, 3, 4, with a remainder of 1, right? 4 with a remainder of 1, just like I did with my math up here. So what does that mean? That means I can send out 1, 2, 3, 4 A's. So I have a to the 4th outside, but underneath the third root, I still have this lonely a. This a right here stays underneath the radical. We can't do anything with it. That actually represented with the remainder of 1. This 4 right here, that's the exponent, but the remainder of 1 is the 1 that's left underneath here. If that was a remainder of 2, for example, this would be a squared underneath the radical, but it's not. It's a remainder of 1. Okay, let me clear out some of my workspace here. Okay, so we found out that the third root of a to the 13th is a to the 4th times the third root of a to the 1st. Okay, so that's the second part here. We're going to go through and do the other thing, the very similar parts to like the third root of b to the 3rd. Well, that's easy. That's just plain old b. And then the third root of a to the 8th. Again, if I think of it, a divided by 3 is 2. That gets me 3 sixths, so with a remainder of 2. So the third root of c to the 8th turns into c squared times the third root of c squared. All right, so now And over here, sorry, the first one we had the third root of 2. So now I'm going to take all of these parts and put them together. The stuff that's outside of the radical will stay outside the radical. So that part will, so the a to the fourth is outside, the b's outside, the c squared is outside. And then the stuff that's underneath of the radical, the 2, the a, the c squared, is going to stay underneath of the radical. So 2ac squared. This is my final answer for this particular problem. It's been simplified down as much as I can. The stuff that can come out, comes out. The stuff that has to stay put, stays put. Please be very careful. It's very critical that you keep the index number the same, right? That it was a third root up here at the beginning of the problem, and at the end, it's still a third root. At this point, I would encourage you to pause the video and try out example D. So pause the video, try out example D. When you unpause the video, I will work through this problem for you. Okay, so I'm going to break this up. I got the fourth root of 486. I have the fourth root of x to the 7th. I have the fourth root of y to the 10th. And I have the fourth root of z to the 13th. Now, I'm going to be honest with you. I'm probably not going to break it up like this. I can kind of do that all in one step. And once you get really good at practicing this, you'll be able to do the same thing. But for now, I'll split it up for you. So let's hear. The fourth root of 486. That is like the fourth root of 81 times 6, because 81 times 6 is 486. So let's hear. That's a 3. The fourth root of 81 is 3. And I'd have a 6 left underneath the fourth root. See how I did that? The next one, let's hear. 7 divided by 4. 7 divided by 4. 7 divided by 4. That's 1 with a remainder of 3. So let's hear. That means that it's going to be x, and then I'll have x to the third left underneath of the radical because it's a remainder of 3. Okay, and then I'll do the next one. The fourth root of y to the 10th. So let's see here. 10 divided by 4 is 2 with a remainder of 2. So that'll mean it's y squared with a y squared left over underneath of the radical. And finally, I have the fourth root of z to the 13th. 13 divided by 4 is, let's see here, no, it's 3. It's 3 with a remainder of 1. So it's z to the third with 1z left over. And that would be my final answer down here. 3xy squared z to the third times the fourth root of 6x to the third y squared z. Okay, so now we have a division problem. X squared divided by the third root of y to the 13th. We're going to rationalize the denominator. So I encourage you to do exactly kind of what we were doing in the last lesson, where we think about what would the best thing to be on the bottom, the best thing to be on the bottom. But with variables, we have to think about it. So this is 13. And right now, if I do 13 divided by 3, that's not an even number. That doesn't work out to be something very nice, right? What, it's going to be 4 with a remainder of 1, right? So that's not nice. We don't want a remainder. A remainder means we still have stuff that's underneath the radical. So I need to figure out exactly what to do here. So let me think here. So what could I multiply y to the 13th by so that it turns into a nice third root? Hey, if it was the third root of y to the 15th, that would be really easy, right? Because 15 divided by 3 is 5, and I'd have y to the 5th on the bottom. So that's actually what I'm going to work towards. I'm going to work towards getting the third root of y to the 15th. So what do I multiply y to the 13th by to get it into y to the 15th? And the answer is y squared. So there is my form of 1, just like I was doing in the last time. Oops, I wrote a 3. It should be a 2, y squared. So that's like what I'm going to do here. I'm going to multiply by that form of 1 that has the third root of y squared over the third root of y squared. So let's see here. The bottom works out nice. The top, x squared times the third root. Well, I can't do anything there. So it's x squared times the third root of y squared. And I don't really care how messy the top gets. That is going to be what's going to stay there for the duration of this problem. So there's my answer. X squared times the third root of y squared over y to the 15th. Now, it's important to note, you can't simplify this fraction anymore. You can't. The y squared is underneath of the radical, the y to the fifth is not. And we can't simplify things unless they are both underneath of a radical or both outside of the radical. So we're done with this problem. That's the final answer. When we have rational exponents, we're going to apply the rule of exponents here. So I'm going to simplify this and do this kind of like I was doing in the other example problems from the previous section where I just had rational exponents. So let's hear. First thing I'll deal with the 16 over 8. 16 divided by 8 is 2. Okay, so that's good. And then I'll look at the x and the x to the 2/3 part, right? So just remember that this is like x to the first over x to the 2/3 power, right? So I don't write the exponent of 1 there. And when I have a fraction and the base numbers are the same, that means that I can subtract the exponent. So 1 minus 2/3. 1 minus 2/3 is 1/3, so this x simplifies down to give me x to the 1/3 power. Okay, so now the y. Y to the 1/3 power, that doesn't match with what's on the bottom, so it's just going to be y to the 1/3 power. And finally, z to the -4th. Let's hear z to the -4th. That's got a negative exponent, so when I see a negative exponent and it's on the bottom, it moves up to the top. So the z, and now it's not -4, it's +4 when it's up on the top. That's my final answer. That one actually wasn't so bad. When we have addition and subtraction and we're mixing what we had just done with simplifying radicals and with variables and all that good stuff, when we put them together, again, we just want to make sure that this matches, that what I'm taking the third root of, everything after the number, right? This part all has to match. That part all has to match. And since it does, I can add these two things together, right? So I can add 6 third roots of x plus 2 third roots of x, and that gives me 8 third roots of x. So that one's not bad. When I look over here at example B, though, if you'll notice, what's in the radical and after the number doesn't match. That doesn't match at all. So what I'm going to do, or have to do here, is I'm going to have to simplify it and see if I end up with anything. So that's here. 16. If I look at this, the fourth root of 3, I can't do anything with, so that's going to stay there. But the fourth root of p to the 6th, 6 divided by 4 is 1 with the remainder of 2. Okay, so 1 with the remainder of 2. So that means I'm going to have p outside, and the fourth root of p squared is going to stay put there. Okay, so the first term is 16p times the fourth root of 3p squared. All right, what about the second one? Let's hear. The 48. Can I simplify the 48? Let me think here. The fourth root of 48. Well, 48 is the same thing as, what's that, 16 times 3, right? So 16 times 3, and the fourth root of 16 is 2. So this ends up being 2p. The fourth root of 3, I can't simplify out that p squared at all, so 3p squared is underneath. Now, if you notice, this matches. Everything after the numerical value matches. Notice I'm including the p in that. So I have 16 p times the fourth root of 3p squared minus 2 p times the fourth root of 3p squared. So because those are like terms, right, everything after the coefficient matches, I can put these together. So it's 16 minus 2, which is 14, and then p fourth root of 3p squared. Be careful with these. If you would ever get something where these are not like terms, right, where what's underneath of the radical or after the coefficient doesn't match, then you cannot combine like terms and your problem would be simplified already. But in this particular case, we can simplify it further. I hope you enjoyed the video. Please, if you have any questions, let me know, but get started on your homework.